Welcome everyone to, I think it's the last seminar talk of the year. And we have Joe Miles joining us today. Joe Miles is a geologist with experience in hyperspectral technologies, working across scales from crystal chemistry to satellite-based mineral mapping. Her talk will highlight recent collaborative projects focused on hyperspectral mineral mapping across Australia. She's working for CSIRO at the moment and is joining in CSIRO efforts towards developing continental-wide mineral maps to support geological mapping and exploration. So the title today is Spectra Across the Scales. And this is Joe. Thank you very much, Joe, for your time and talk. So the floor is yours.
Thank you. Thank you for having me. Apologies, I'm at the very back of the room. I'm next to the power outlet, but hopefully my voice travels wherever it may be.
Can you guys hear us okay? Thumbs up?
Yeah.
Awesome. Thanks for the introduction. So I'd like to begin by acknowledging the Larrakia people as the traditional owners of the land that we're meeting on today and pay my respect to their elders past and present. So for those of you who may be unaware who we are at CSIRO and the work that we do, we are Australia's national science agency. And really the sole purpose of us is to provide benefit to Australia via research and innovation. So I work in the Discovery Programme that's situated in Perth within the larger Mineral Resources Research Unit. And we're dotted all around Australia. And before my job at CSIRO, I was in exploration in Arctic Sweden. And I've been in my role for currently 2 years now. And I work with spectral data sets to help answer questions we have about mineral systems. And I work a lot with geological surveys and junior explorers. So I thought I would get to the nitty-gritty. This is a little bit boring and dry, I'm sorry, but it's needed, because understanding the electromagnetic spectrum sets the stage for how we use spectroscopy at every scale. From that microscope all the way to that regional continental scale mapping. And we actually only are able to see a very small part of that electromagnetic spectrum with our eye. And we have technologies that go across the visible, near, short, mid, and thermal. And we have the active minerals there in yellow. So for example, the visible near infrared is really helpful for our iron oxides and our rare earth elements, such as neodymium. The short wave is really well characterized by clays. The mid is a little bit of a dark art at the moment because we only just have the high log of 4 and handheld FTIR devices that are scanning that part. And so we're still trying to work out what's happening in this region. And then into the thermal there, which is good for our silicates, so our quartz, our feldspars. It's really helpful with spodumene. And in the green along the bottom there, we've got some hyperspectral technologies that really use this fundamental theory. And we have the satellite sensors, Prisma, EnMAP, and EMIT. We have handheld devices that can be used both in the field and the lab, such as the ASD, ORExpert, and the FTIR. And then we've got the high log of 3 there, which is what we have here at NTGS, that captures that visible, near, short, and thermal. And more recently, the high log of 4, which has just been commercialized by Epiroc, scans the entire wavelength region. And that is the first and only drill core scanning device that can do that. So spectroscopy is one of the only tools whereby the fundamentals, or that theory behind the technique, is pretty similar for all the technologies. And so that allows us to work at various scales, resolutions, and more importantly, it helps us to integrate those data sets to have a greater understanding of the mineral system that we work in. So very simply, when it comes to reflective spectroscopy, we have a light source. Now that might be a halogen bulb in a lamp, or it could be the sun itself. And it makes our way to the mineral, so our target there. And it reflects, absorbs, and scatters light. And this happens at diagnostic wavelengths that are very diagnostic of the mineral itself, almost like a fingerprint. And that's unique and recognizable to that particular mineral. And then it makes its way into the detector where it's captured, and we see it as a trough within the visible near, short and mid infrared range. There is a spectral feature at a certain wavelength that we know is well characterized to represent a certain mineral. So to make this more concrete, I just want to kind of show how these principles apply to real minerals like spodumene. So on the left here, we have the visible near, short and mid infrared. And this region is really dominated by volume scattering. And so the light goes into the mineral, it bounces around, it hits intergrown white micas, and then escapes the sample. And so here, generally, we're seeing troughs in the data set, whereas when we go into the thermal, it's more surface scattering phenomena. And so that's really, we're not capturing any information. And so you might, anyone that's familiar with spectral might ask why we're getting features that are not associated with spodumene in a spodumene reflectance library sample. And that is because in the volume scattering part, we're actually getting signals from gangue. And so this is really important to understand. And often when we interact with industry, they talk to us about an aluminium or an iron-rich spodumene, but it's most likely not. It's actually probably the gangue that the technology is interacting with as a result of that volume scattering in the visible near, shortwave and mid-infrared portion. But also it's a really nice example of how these data sets across the wavelength range can complement each other to give you the bigger picture. And maybe if you was just to focus on one region, you wouldn't be able to see that in its entirety. And that really brings on to our reflectance database, which is freely available and highlights the real need for a good and robust reflectance database for both research and industry. This is accessible online, and you can search by the mineral name or chemical formula. You can view the high quality spectra, download them. If you're a chemist and you want to see this in wave numbers, you can also download it there, or if you're a geologist working on wavelength. And it supports both the NVCL community, but also industry that has some of these instruments. And what's different about this particular reflectance database is that all the spectra have come from some kind of peer-reviewed journal or report. So you're actually able to trace back the mineral and its origin, which you can't always do with spectral reflectance libraries. And so we started at the spodumene crystal. So we know that we can get some influence from some gangue there. And so I wanted to kind of go in this talk, go up and build upon all these different knowledge and scales before getting to the more regional case study. So now we're going to very briefly touch on graphite and lithium pegmatites. So it's an example close to you in the Pine Creek origin. And this was a really recent case study done by my colleagues. And they were looking at the flake quality and also what other things will make it to the processing plant. And they deduced that using Raman alone for grade quality and FTIR alone for that gangue mineralogy identification and characterization wouldn't be helpful. And actually, it's when the marriage of those two data sets come together that you're really able to make sense of that geological story and to actually inform on some of these quite important decisions to be made when it comes to the characterization of the ore deposit and the future processing pathways. So I recommend looking at that particular open access paper if you want to kind of know a little bit more. And when it comes to other things such as lithium pegmatites, we started at that spodumene crystal. And what I really want to emphasize is this awesome database, the National Virtual Core Library. And there are thousands of drill core publicly available for you to download, to interrogate. And this is all free pre-competitive data. And my colleague Carsten, he wanted to understand exactly how do lithium pegmatites vary across Australia, and potentially why are they different globally. So there's a publication coming soon, but I thought I would just take some of the snippets really that I thought was pretty important. And this didn't require any, this just was in the data. And there's lots of other projects and master's projects that can easily be created as a result of this database. So we're going to talk a little bit about the high logger. And remember, we're able to see the silicates there because we have the thermal infrared, which is super helpful for our pegmatites, but also we've got that shortwave infrared, which is helpful for our clays. So we're going to talk through the plagioclase, the white mica, the spodumene, and the chlorite epidote. And we'll also talk about why scale is important and what that can infer. So we'll start with the Dorchap Dyke Swarm in Victoria. And this is a relatively narrow pegmatite. It's only about 4 meters wide. And what we're able to see very easily is when we look at the composition of the white mica, so that's its wavelength position, is that it's aluminium rich within the pegmatite itself, but it actually has a very narrow aluminium pore halo. And you might be able to make out just kind of the yellows and the oranges just on the very edge of that pegmatite there. So you've got a 4 meter pegmatite and really a 1 to 2 meter halo. And so that tells us when we're, exploring with things like remote sensing, that that's really beyond the resolutions of some of our capabilities in the satellite space. Buchanan's Creek in Queensland, aluminium rich again, white mica in the middle, which it's very diagnostic of fresh, and it's got a very narrow aluminium pore. So even though this particular pegmatite is bigger, it's 12 meters, it's still only got a very narrow 1 to 2 meter wide halo. And so there isn't really a correlation between the pegmatite size and the halo size. And then if we go to Londonderry in WA, this particular hole has 2 discrete pegmatites. And what we're seeing here is iron-rich white mica. And when we look at the correlation with spodumene, what we're actually deducing here is that it's not a good sign. It's altered, and the lithium mineralogy has likely broken down and gone. And we see this again in little oxidized or faulted parts of the pegmatite itself, where we have this iron-rich white mica associated with the spodumene. But what is interesting about this example at King Cole in WA is that it's a rather large pegmatite at 24 meters, and there's a chlorite epidote. It increases in abundance around the pegmatite, a propylitic halo. But a big challenge, obviously, just from looking at high logger data is how we would discriminate the alteration of that pegmatite from background metamorphism with the chlorite and epidote. And we see something very similar at Pilgangora in WA. So hopefully that just gives a bit of an insight into what you can find with some of these freely available pre-competitive data sets to inform about some of the mineral styles that are out there but not necessarily publicized. And so now we're going to upscale that a little bit to kind of the camp regional scale. And so just to remind you, again, we have in this particular example, we have the sun as our light source. It's hitting our ground, and each material that it hits has a certain characteristic, a wavelength. So we've got vegetation, water, and regolith, our signals there. And it then gets captured by our imaging sensor and detector. So we get an RGB image at the same time. And what I really want to highlight here is on the left is what I hope is quite a clear explanation for the difference between multispectral and hyperspectral data sets. So for example, ASTA is a multispectral data set, and I'll show you some mineral maps there in a moment. But these are, quite broad bands, and they're not continuous, so they're only looking at certain wavelength regions. And when we look at hyperspectral there, we've got hundreds of narrow we've got a continuous data set and they're contiguous. That means they're overlapping. And so we're able to capture a significant more amount of information there than what we was with multispectral. So we've gone from being able to map mineral groups in the multispectral to minerals themselves in the hyperspectral. And back in 2012, CSIRO released the ASTA continental mineral maps. And this still remains to be industry standard. When we speak with explorers, this is free, pre-competitive data sets, easily downloadable. They're easily able to understand the coverage over their tenement. And we wanted to understand the impact of this and whether remote sensing it was still wanted by the mining community. And so RTI International did an impact assessment just this year that determined a benefit cost ratio of $363. So what that means is that every $1 that the Australian government put in, that's GA, the Geological Surveys and CSIRO, it returned $363 back. And that QR code there goes to the report and to the blog post where we talk about some of these findings. And now it still remains to be the industry standard, but we've moved on a little bit since then. So since 2019, Prisma, NMAP and EMIT have come on board, and these are hyperspectral satellite sensors. They're all freely available because they're research vessels. So we have the Italian Space Agency, the German Space Agency, and NASA JPL. So Prisma and NMAP are 30-meter pixel sizes. EMIT is the 60-meter pixel size. And if we was to compare them with some other sensors you might have heard of, so for example, Landsat and Sentinel, they've been going for a long time, but generally what they're good at is determining surface patterns, so things like landscapes and regolith. And they are very good time series data sets. So if you're wanting to monitor something like wildfires, really great use for that. The mining industry, though, doesn't see much use except for things like tailings monitoring. Then we've got more of our multispectral in the middle, and these are mineral targeting mineral groups. So we've got the ASTA and the WorldView 3 there. And then at the very top there, the spectral resolution of EMIT, Prisma and NMAP satellites. They're looking at mineral species and their chemistry. And also we've got the HIMAP system, which is HiVista's airborne sensor that is situated in Australia. And so what you'll notice is that the spatial resolution of ASTA and some of these hyperspectral satellites is exactly the same, but I want you to remember the difference between the multispectral and the hyperspectral in terms of the amount of bands, because you'll see a real difference in those maps that I just showed you from ASTA to what we're working towards now. And if you're not aware, hopefully I will make you aware with this slide, but Australia is covered by hyperspectral satellite imagery. And we've made this educational layer in our XT portal. It's freely available to go in, have a look, click on and off different satellites to determine whether a tenement or your field area is covered. And then you're able to go to those links in the previous slide from Prisma, NMAP and EMIT to download the imagery. And what's good about this is also that you can click on each of these individual footprints and it will tell you the date. If you're interested in a particular season, that could also be very helpful for you. And so this one's a little bit dated, but this was an early proof of concept that we did. So you can see on the left there, we've got the aluminium OH group content that we're mapping with ASTA. And on the right there, this is our Prisma and NMAP mosaic. And you can already see a significant improvement in the geological domains that we're able to identify just because of that increase in spectral resolution. The spatial resolution, the 30-meter pixel size, remains the same. Unfortunately, there's a lot of gaps in this data set. We have since updated it, but a lot of that is due to cloud and green vegetation. And so we've now set up an infrastructure in CSIRO that allows us to download the most recent data sets, and we're able to hopefully very shortly filter through seasons, so that we can make sure that we have the barest of Earth when we are capturing this imagery. And a little case study about the Pilbara Craton in WA. So what I really want to highlight to you is we've got these kind of pink to red domal features. I wonder if you can see my pointer. There we go. Yeah. It's a little bit slow, but and these are granitoids, and they're bordered by these sinuous greenstone belts. And this particular project with GSWA and Cobalt Metals was instigated because there is a link between pegmatites and the granites, but the pegmatites generally occur within the greenstones. And so we wanted to see whether or not we can mineral map for lithium pegmatites, but you have to remember that spodumene isn't seen with these satellite sensors. That's only something that things like the Highlogger can see, because a lot of the technology for remote sensing is in that visible near and shortwave infrared part. And just for comparison, this is what ASTA looked like when we released it in 2012. And this was really great in the day. It was a real,
breakthrough.
A breakthrough, absolutely. Processing so much data, streamlining that, but you can obviously see there's a lot of striping, and there's incomplete coverage as a result, of just the nature of the ASTA data. And really the improvement there is with our Prisma Craton map. And you're starting, I appreciate at this scale, you can make out these domes. There is a variable response in aluminium sheet silicates within the greenstones itself. And that's related to the white mica and kaolinite and aluminium smectite. And we've kind of got a research student at the moment that's looking at what's happening within the domes themselves, because there are some patterns of white mica, kaolinite and aluminium smectite. And we're trying to, relate them to certain linear features, certain structures. There's a lot of information within this data set. And this is all available by that QR code with the GSWA bookshop. It's a report that details all the processing, but also all the mineral maps for the Pilbara Craton and the Gascoyne region are available as free pre-competitive data sets. So hopefully I've demonstrated to you that spectroscopy is one of those tools whereby, the fundamentals of light and reflectance is generally the same for all of these technologies. And it allows us to integrate the data sets. So what happens? What does that look like when we're trying to understand a mineral system? So here is Rocklear Dome. This was in 2021 by my colleagues, but it's one of the only data sets where we have all of this information publicly available. And it was used as a test data set for a few things: data mining for exploration and mining itself, integration of independent geoscience data sets, so hyperspectral, geochemistry, geophysics, resource modeling, and also different approaches to routine processing of hyperspectral data. And that report and data is also freely available for you to download, play with, and kind of understand what you can do with spectral data. So finally, this is our website if you want to read about any kind of case studies that we've been working on, and the XT data portal if you want to play around with some of those layers. Those Pilbara and Gascoyne mineral maps will soon be in the XT data portal, and as well with the interactive footprint layer, you're able to use the coordinates QGIS plugin, and so you're able to very easily get those maps into your QGIS workspace. And that is everything from me. Thank you very much.
Thank you very much, Joe. Any question on the online universe, the Zoom universe? If not, I'll kick in with some questions or comments. Fantastic, thank you. This is a great for people that are not aware of these technologies. This is a fantastic tool, and nowadays is more and more online, free, available, open source platforms that people can actually access and mine to things. And talking about that data mining, how much of machine learning and AI is involved in these new ways of dealing with these data sets? Is that part of your workflow, or your people are collecting this data?
So actually, a lot of these algorithms are based on the fundamental science. And so with, especially with a lot of our mineral mapping, we're not using ML or AI.
Yeah.
Now, we do have some researchers that kind of do spin-off projects in that space.
Oh, okay. Yeah.
It's not my field of expertise, but in terms of machine learning, so for example, data mining the HiLogger database and looking for occurrences of heavy mineral sands, things like that.
Yeah.
And then using the principles of what they may look like in HiLogger to determine where else that might be occurring.
Yeah.
There are definitely lots of avenues. Not off the top of my head, it's out of my
because I can imagine
expertise.
Since this spectral equals this mineral based on, I imagine there's a bit of a probability involved or statistics involved. So, okay, this is how close is this spectral to the standard for this mineral, and there must be a probability involved there. So I imagine when the software that in this case is TSA, what's the name of the software?
So it depends really. We use TSG. But also then we use Python, which we've upscaled from Envy for our regional work. But with TSG, you're able to input all of this data. And
guess from there.
Yeah.
So the second question was about I've been using the MyLogger from CSIRO. Fantastic, I love it because it just basically it does this exploratory data analytics that is the first pass, and it shows beautifully some of the first pass interpretations this way. So it's super user friendly as well. So well done, CSIRO. I think on that one is free and it's open source.
Yeah, it's on the XT data portal.
Yeah, fantastic. And the last questions, using vegetation as proxy for rock types, like when we were discussing before about the Pine Creek and how difficult it will be to pick up rock types, but it's being done in some way, studies on using differences in vegetation as a proxy for.
Yeah, there certainly has been some case studies. I know in Canada, for example, they use the knowledge of certain lichens and upscale that into satellite imagery.
Oh, okay. Yeah.
To map the certain rock units.
Yeah.
I guess it's not something in mineral resources we've ever been asked to explore, but there's certainly capability in our agriculture and our environment research units that use these data sets. So I don't see there being a problem in the transfer of that knowledge to actually what lithology does that reflect. It would probably need a little bit of training data, and that using your geological map maybe as a base map.
Yeah, and learn from that.
Yeah, as a first pass, and then seeing how you would improve it. And also, I guess we'd actually probably need to build a database of the various vegetations that you expect.
Yeah, it's probably
some might be accumulators of certain elements. I think you can, see some rare earths sometimes in the leaves.
That in copper exploration they use some specific.
Yeah,
that
and I think
grows.
so with, for example, neodymium, you can actually use this technology. But I wouldn't know the quantity needed in a leaf to see it from space.
Or detecting a specific species that we know grows in specific soil types associated with a lot of proxies.
And I think if it's densely vegetated enough, and you got to think about the pixel size of 30 meter. Does that particular vegetation type contribute enough to that pixel to dominate it, so we get a very clear signal?
Yes.
And then it just needs to be 1 pixel really, and then we can understand, okay, if we go to a neighboring pixel, what mixtures are we now seeing with that vegetation?
So exciting. Exciting. Who's there left? Annette, Jessica, Belinda, any question?
Yeah, I did have a couple of things that probably lead into one. Thanks, Joe, for your presentation. It was nice to hear more from you. I was just wondering what the penetration depth of the hyperspectral data is. I'm not too familiar with hyperspectral data. So I guess leading on from that, how does it go with cover? We were kind of talking about that earlier, but does that mean if there's cover, like the data is useless underneath? And then what about outcrop as well? Like, do you need outcrop of certain units to see them in the data?
Yeah, so it is a surface technique. It doesn't penetrate all that much. And so it's a really good reconnaissance tool. It has been used for mapping lithology for regolith and landscape, I would say. Now, in terms of lithology, outcrop is preferenced, it's more crystalline, or residual regolith, that can also be helpful because that has a similar crystallinity generally to the underlying rock that it reflects. The difficulty is with transported cover really, and the mixed signals that you would expect to find. And also you notice a lot of, I guess, geomorphology plays a role there in regards to, sheet washes and flash flooding in places. That really will influence what you see at surface from season to season. And I guess that's why time series is slowly becoming available with these sensors. Did I miss a question?
No, that's all good.
That's all, yeah.
Thanks.
If that's it, we'll conclude for now. Thank you again very much, Joe, for joining us today. And I'll see you everyone next year. Be ready because it's like more talk series are coming next year. So stay tuned, and thank you very much everyone to come here.